country, eh? Wet country. Power country. The country of drifting clouds and falling water. Mountains turning clouds into rain, rain into lakes, building reservoirs of power. This is northern British Columbia, hundreds of miles from civilization. 3 years ago, we came here to put the water to work. 6,000 of us from all over the world, but mostly Canadian, or Canadiens, as we say it in Arvida, in Quebec, where I come from. I'm a long way from Arvida now, but the job is the same. Putting water to work, making power, making aluminum. Kijimat, the city we built, still growing. The smelter, still growing. "50 miles away at Kimano, inside that mountain, is the powerhouse that feeds the smelter. My office is down there too, but I don't spend much time at that desk."
I guess Mr. Marcotte didn't expect you till the afternoon flight. Mr. Mitchell, this will be your desk. And Mr. Marcotte said he'd have a telephone for you in a day or two. In the meantime, you'll just have to use his.
Generator 4.
Well, you'll be supervising the installation, won't you?
That's right.
If you want me for anything, my local is 102.
Where can I find Mr. Marcotte?
Well, I'm afraid you can't, not unless you've got wings. See, here's a model of the whole area. Now, Vancouver would be, down here, be underneath the desk, 400 miles south of here. Right now, we're here, and Mr. Marcotte's over here at Kenny Dam, which is 150 miles away. He flew up this morning to check water levels and make a routine inspection.
Jobs like this must keep him on the hop.
Oh, he takes it all in his stride.
Nothing to worry about up here. Levels rising. Water building up behind the dam a little more every day. All we got to do is keep an eye on it. The 3-pounder this time, Jim.
Last one you'll have time for. Here she comes.
Soft touch, this engineering.
You kept me waiting.
Power control, not good.
Marcotte. Power control, go ahead.
Leaving Kenny Dam, estimating west at in an hour.
Right, John. Hope you got a fish.
You know me down there.
I guess you people ought to be able to fish this lake. You made it.
You come out to the lonely country and you work with the mountains and the clouds and the falling water if you want power. The dam looks like it's always been there. Looks like part of the country now. Hard to remember what it was like when the big machines were dumping rock to make it.
No holes in the dam? No holes in the dam.
Little lake that used to trickle east, growing into one big lake now, turning back west to run the generators.
Filling up nicely.
All the time, bigger every day.
Well, I guess you're all set now.
The tunnel gate, where we sent the lake underground, started water for the turbines, 10 miles west and half mile down.
West Tatsa intake. Marcotte? Yeah, I hear him now.
Okay, Mike. Send the helicopter at 2. I invited myself to lunch, Mrs. Hughes.
Good. We'll be ready in 10 minutes.
Let's have a look at the flow chart.
Okay, you're in the gatehouse.
I checked the level at Kenny Dam this morning.
You did? How's she coming?
Building up all the time. We're never going to have any worry about water. Every day, millions of gallons of water flowing into that 10-mile tunnel, then dropping half a mile through the penstocks to the turbine pits. And you hardly see it move.
Mr. Marcotte shouldn't be long now. He's finished his task and the helicopter's gone for him.
Good. Oh, Miss Wilson,
Yes.
how long does it take the helicopter to come from
Tatsa.
Tatsa?
That's right. Oh, about 20 minutes. If you like, I could call a jeep and you could meet him on the landing field.
Fine, I'd like to do that.
All right.
Herb give you a good lunch?
Mm-hmm.
Trout. Fine. I had a ham sandwich.
You'd never know we'd built a 10-mile tunnel through that rock. You'd never know the lake up there was feeding the turbines down below. It makes no difference to the mountain. 6,000 men, 3 years' work to scoop out its core and send the river pouring down through its middle. And it makes no difference to the mountain.
Your new man's waiting down below.
Oh, good. What's it look like?
Oh, like they all look when they first come along.
Nervous?
A little bit. This place is kind of big.
Well, relax. Water's up there making the power. Kitamat's over there across the mountains making the aluminum. All we got to do is put in more generators.
Makes it sound pretty simple.
It is now. Wasn't quite so simple at first.
Were you here from the beginning?
Company brought me from Avida. I was raised on the stuff.
Okay, Mr. Mark.
First toy I ever had was an ingot. Power.
We must be half a mile inside of this mountain.
No, just a quarter mile. This is Mitchell, my new assistant. Bill Carson, Don Michaels. Command O power control room. Number 1 generator, number 2, number 3. And here will go number 4, the one you'll be working on. After that, 12 more when we get ready. You're listening to my kittens purring. Come and meet them.
Number 3, stand by. You are enough to run the smelter so far. Number 4, your job. Looks like a big job, and more to come. 12 more. Room to grow, eh? One of the biggest powerhouses in the world. Scooped out of solid rock in the middle of the mountain. 5 stories high, 700 feet long, and still growing.
2,400,000 horsepower.
Waiting to be used in the lake up there. We only use 600,000 so far. Let's go down to the shaft room. Up there! Last mile of water pouring straight down through the mountain. She hit the bucket in the turbine pit. And what happened?
I know, nobody could. I said now we go find your place to sleep.
Two months on the job and he's right at home. I got me a good man.
Call from Kitamat, Mr. Marcotte. Mr. Phillips wants you to fly over right away.
Oh? Tell him I'll be there right after lunch, Bob. How are you making out?
All right here. How is it with you?
I'm not sure. Mr. Phillips wants to see me. Big boss, eh? Is that bad? Good, I guess. Only I think it's going to mean a change. Always changes around here.
Look at that blasted mist over there.
Blasted mist. That's water. That's what fills the lake and runs the plant. Mist and cloud and falling water. If this country wasn't filled with it, we wouldn't be here. That's power, and we want it.
Look, what I want to know is, are we going to eat in Kitimat or are we going right back?
Oh, you eat. I'll go back in the helicopter.
Long way from home, aren't you?
I'm waiting for my daddy, Mr. Marcotte.
Hey, now I know you. Gordon Robinson's boy.
My daddy works here.
That's right. Tell the chief I'm coming over to the village to see a soccer game one of these days.
And tell Mr. Kennedy I'd like to discuss this directive with him before we put it out. Oh, Commissioner, I'll be right with you. I've made some changes in this draft, but it's all right now. Well, Jean, how are you?
I'm fine, thank you.
I suppose you know why I called you over.
I guess so.
As soon as number 4 is installed, I want you to come over here and help run the place. It's a nice promotion.
Long way from the powerhouse.
30 minutes by plane. Commando's only a normal job of power expansion now. That new assistant of yours is working out very well over there. Jean, you're a senior man now. We need you over here.
So, already I'm a senior man.
Things happen pretty quickly in this place. Have you seen the town site lately?
Not for a while.
I suggest you take a look at it right away. You'll have to have someplace to live. And if you have time, drop in and see me before you go back.
I will, if I have time. And thank you very much.
Good luck to you, Jean. Oh, by the way, Kennedy's showing a visitor around the plant. You ought to meet him. He's a pulp and paper man.
Pulp and paper, eh?
Yes, someday aluminum may be only one of the industries in Kitimat. You'll find him somewhere in the smelter.
I'll go right over. Seen Mr. Kennedy, Jim?
He might be in the basement of the rectifier room, Mr. Marshall. He was on his way to the pot lines.
Hello, Jean. This is Mr. C.P. Johnson. How do you do, Mr. Johnson? Pulp and paper. He's thinking of starting operations up the valley. How's that new man working out?
Fine. He's fitting in like a glove. Best not look at him. No danger, but you get one almighty flash and a bang like a cannon. If anything happens on the circuit, 200,000 volts falling in from Kimano. Mr. Johnson seeing where they go to work?
That's what it looks like before the power gets to it. The crust breaker.
We're building 8 more pot lines here. At Kimano, we're installing the generators to feed them.
Turning out a lot of aluminum.
A lot of aluminum. 80,000 tons a year. And it's only a beginning. Everybody wants more, always more. Thousands of ingots piling up, moving out day after day, and never enough. We scoop the brown ore out of the earth in Jamaica, in British Guiana, in West Africa. Turn it into the white dust. Bring it here in the freighters. And here, power goes to work on it. The dust becomes a silver river flowing into the molds, hardening into ingot, moving out to the world again. And here in the wilderness, a city grows. Better find yourself a place in that.
By the time you were in the market for a house, who's the lucky girl?
Who knows? I'm busy sorting out the applications. But now I got an assistant. I have time to think about it.
Want to look at the map or the town?
The town.
Okay.
Every time I come to Kitimat, it's bigger. 3 months ago, the Bears lived here.
3 years ago, they owned the whole place. 6,000 people here now. Be 12,000 in a year, probably 50,000 in 10.
It would be good living here.
You want to come back and sign up?
First, I better sign me up a girl.
You'd make a better deal if you had a house.
Step on it. Helicopter's waiting.
Okay. Doing over 30 feet. Look, John, don't I get any favors? Sure. My autograph. There you are. 10 bucks up the spout.
Charge it up to civilization.
Pretty good enough.
To Kitimat, 50 miles across the mountains of British Columbia, we strung a power line. And I helped. Me, Jean Marcotte of Elvira, whose grandfather was lumberjack. It is something to remember.
What?
Nothing. Home, James. Follow the line.
down the current transformers, take out that equipment, and close the cage.
Did you check the erectors and phase out this unit?
Didn't want to waste the time.
Hey, you hold it!
You can go, Eddie. What's the big idea? There's not one chance in a million of anything going wrong with that.
What do you think? We got signals all over the place for? Why do you think we put cages around those tigers? What we got rules for? Because we don't take one chance in a million. If you'd been here from the start like me, you'd know the chances we had to take. But we don't anymore. Now we play safe. And you play it that way or you take the boat. See?
Yeah, I see.
Okay, get back to it.
Mitch, maybe it was only one chance in 2 million. But don't take it. Number 4 nearly ready. Just another generator. But it's got to be right. When you're playing with all the power we got stored up in these mountains, you get things right. I know how he feels.
Oh, just a moment. He's just come in. Yes, can I ask him about number 4?
Look, I told you we'd start her up tomorrow, and she's starting. Sure, everything's fine. Bye. What are you worrying about?
Just checking up.
You checked everything 4 times already. And what's more, I did too. I kept my eye on you. I just told Kitty Matt everything's okay. And when I say that, I mean it.
Keep wondering if I slipped up anywhere.
You haven't. Tomorrow afternoon at 2 o'clock, we'll be operating 4 generators, thinking about number 5.
All I'm worrying about right now is number 4.
Look, Mitch, will you cut it out? If you weren't good, you wouldn't be here. Everything's going to be all right.
Fine. Tell me that tomorrow after she's started.
Command and control.
Kinemat's asking when we're going to start up.
125. Where's Mitchell?
The turbine pit.
My card says 125.
Needle valve. All okay. Deflectors? Check.
They look like they'll spin when the water hits them. Manifold drain closed? Yes. Ready? Ready. I'll be in the control room. Downstream valve open.
Bypass valves open.
Bypass valves open. Right.
Downstream valve closed.
shear valve.
Okay. Hello, Kitamat. The shear valve's open now. It won't be long now, boy.
She's open. Okay, bring down that water.
Running at 200 RPM.
Set her up to 250.
Okay.
Did you check the cooling water?
Yes, everything is nice and cool. $320. $323. $325. Now at 327. Closing G4 disconnect.
I'm putting her on. Okay, cut her in.
Today, the map of Canada shows the new town of Kitimat on the rugged coast of British Columbia, where a new aluminum industry is in operation. The first stage of this vast project was completed, and the first aluminum ingot was poured in the summer of 1954. This project to smelt aluminum needed tremendous quantities of electrical power, and the development of this power was a major part of the project. It required the building of a dam to impound the waters of a river. The driving of a 10-mile tunnel through a mountain range. The hewing of a powerhouse cavern out of the solid rock. The installation of machinery to produce the first stage of an eventual 2,400,000 horsepower. And finally, it required the building of transmission lines to carry this vast power across 50 miles of mountain country. The accomplishment of this transmission link was one of the major engineering achievements of the project. The best route for the transmission lines lay over Kildala Pass. The 5,000-foot elevation is reached from the valley floor in less than 3 miles, a very steep climb for a transmission line. The first thing to do was to check weather conditions at the summit. Test towers were built to support a short span of cable. The purpose was to check ice loading, snow and wind conditions during the winter months. At the same time, a tote road from the valley was begun, although there was doubt that it could be completed in time. 2 winters that followed provided data on which to base structural design. Even to the casual eye, it was obvious that spans would be long and that loads, both electrical and structural, would be heavy. There was space in the pass for 2 circuits. Each would have to be capable of carrying 1.5 million horsepower. Conductors 2 1/4 inches in diameter and with a tensile strength of 135,000 pounds would need towers 120 feet high to span valleys and glaciers. There would be large changes in elevation and direction, as well as great variations in spans. The towers would have to carry combinations of forces up to 57 tons vertically per suspension point, which represented the weight of the conductors with maximum ice load. 43 tons per suspension point across the direction of the line, which represented changes in direction of the conductors at the tower and pressure of wind on the line. 22.5 tons along each conductor, representing tension variations due to ice loading. And 12 tons at any one suspension point in case of a broken conductor. In addition, there was the accumulation of rime on the tower itself. There was the pressure of snow against the legs. Snow pressures up to 30 tons per leg were anticipated to act down the line of 40-degree slopes. This was no ordinary transmission line. Most of the route could be traversed with conventional double-circuit towers. A right-of-way up the Kildala River Valley was cleared of timber, and construction of this section was soon underway. But the size and weight of towers needed for the steep climb up Kildala Pass called for special consideration. Here was an opportunity to show what could be done with aluminum to simplify and speed construction. It was decided to run one of the lines using aluminum towers. The best design for aluminum need not be the conventional lattice structure. Let us look at basic requirements. 3 conductors had to be supported at points 30 feet apart and about 120 feet off the ground. A beam was necessary. This beam would need to be supported between the conductors to carry their weight and resist pulls along the lines due to uneven ice loads. For this purpose, 2 A-frames would be required. Forces across the line due to change in direction of the conductors and due to wind would require a diagonal brace. If these forces were greater than one leg could carry, a second diagonal could be added. This was the basic theory. We now clothe the skeleton in structural elements best suited for the purpose. A box girder for the crossarm to take the bending forces, and thin wall tubes for the legs to take the compression forces. We make use of the rigidity of steel to distribute loads evenly in the aluminum structure, to distribute the conductor forces into the crossarm, to transfer forces from the crossarm to the legs, to distribute the forces in the legs between their respective anchor bolts. The loads would be so large that this unusual type of structure would become worthwhile. Its principal advantages were simplicity, lightness, ease of transportation, and freedom from ice accumulation. Naturally, the tower would have to be thoroughly tested before it could be accepted. The test was remarkable on two accounts. It not only involved the greatest forces ever applied in the test of an aluminum structure, but they were also the largest loads ever applied to a transmission tower of any kind. Combinations of forces in a number of tests simulated the worst conditions of service. These blocks compounded the strength of chain blocks, which were operated at a safe distance from the tower test area. The testing went on for 3 days, applying load combinations to simulate all conditions of service. Surveyors recorded deflections of the structure at all important points. The prototype behaved exactly as intended, and the decision to use the aluminum towers was confirmed. The aluminum towers were soon in full production. As a material for structural work, aluminum has a number of advantages. The light metal is clean and easy to handle. It can be fabricated with machinery you would expect to find in any well-equipped plate shop. These transmission towers were made of Alcan 65ST aluminum alloy. All parts were formed cold so as to avoid impairing the properties given this alloy by heat treatment. High-speed woodworking bandsaws cut aluminum quickly. Joint rings for the leg sections were rolled and welded. The parts were shipped by barge to the site of the project. Upon arrival at Camano, they were transferred to storage areas at base camps of the pass and moved by high line to the sites. Field assembly of the towers was straightforward. First, one leg of each A-frame was built up from prepared footings. The opposite legs were similarly assembled until the A-frames were jointed. While the diagonal leg was being built, the cross arm was assembled on the ground. Finally, the cross arm was lifted into position in one piece. Two leg sections were joined together and lifted in one piece for bolting onto the shoe. The steel shoe had already been set to grade and held by 15-foot anchor bolts grouted into the rock. Two special aluminum gin poles were used in the erection of each tower. These were of welded construction, strong enough to lift the heaviest piece of the tower. Ladders inside the legs and on the gin pole gave the men firm footing and allowed them both hands free. The aluminum towers were erected without an accident. which is a tribute to the adaptability of the men to an entirely new method of erection. Gin poles were clamped to the top section of each leg by 2 steel hoops. The thrust from the load was taken in bearing against a leg joint. The outboard sheave of the gin pole allowed loads to be lifted clear of the structure. The work progressed safely and quickly. Legs went up in a succession of similar operations, which crews soon reduced to a system. Joints were closed with clamps on the inside. The crossarm rolled up on dollies, and winches were synchronized to keep the dollies on the legs. There was no need for anyone to be on the tower as the crossarm went up. Extensive prefabrication greatly reduced fieldwork. Compared to a lattice tower of equivalent size, this structure has 1/10 the number of parts assembled, with half the number of bolts. Furthermore, there was a high degree of interchangeability. All leg sections were 38 inches in diameter and varied only in wall thickness from 3/16 to 3/8 inches, according to the loads. Special measures were taken to prevent the crossarm swinging in suddenly and bumping the supporting jibs. When the crossarm was in position, dollies, jibs, and other erection gear were dismantled. Handrails on top of the crossarm were left on until the line had been strung. With the towers built, half the job was done, but the stringing of EMU, the world's largest high-tension conductor, presented another challenge. However, the transportation of heavy stringing equipment could now be simplified by stringing high lines from the towers. This 2,500-foot span was the longest in the line. Tractor power was used to string the cable. The conductor was strung under tension. Communication by radio and telephone kept the work under control. Conductor from the reel was pulled through travelers on the towers. First, it passed through a tension machine, which maintained a steady drag against the winch. When one reel came to an end, the next was threaded through the tension machine by fitting a basket come-along. This type of come-along held firmly even on a conductor of this size. Both splices and dead ends were made with standard compression joints. The procedure was conventional despite the fact that there were 4 layers of aluminum strands. First, the steel core was laid bare and painted with zinc chromate paint. To ensure good electrical conductivity, each strand was carefully cleaned with steel wool and coated with oxide inhibiting compound. The strands were carefully relayed around the core. The aluminum dead-end body was a close fit on the conductor. The strands were kept tight by rotating it against the direction of lay of the strands. It had to be slid onto the cable beyond the joint before the steel dead-end body could be fixed to the steel core. A 135-ton hydraulic compression tool was used. The steel joint was now completed. A motor-driven hydraulic pump speeded the work. The aluminum body was slid back into position and packed with oxide inhibiting compound and sealed. Finally, the aluminum body itself was compressed. The finished dead end was attached to the insulators, and the whole assembly was then pulled up to the tower. The lifting of 6 parallel strings of insulators required special care to prevent them from knocking together and smashing one another. Wooden spacers kept the insulators apart until they had been connected under tension to their anchorage on the tower. This operation had to be done with meticulous care. The clevis bolt slipped home and the span was made. This insulator assembly weighs over a ton. The protecting spacers were cleared from the insulators and the job was complete, except for the removal of the come-along. Every advantage was taken of weather to string the line. The work was often an adventure as well as a job. A manhole in the bottom of each leg gave access to ladders inside. Doors on the A-frame heads opened below ladders on the cross arms. And so the stringing went on through the short northern summer of 1953 to be completed the following year. If the creation of this transmission line was exciting work for the men who designed it and for the crews who built it, so it was also for the cameramen. who climbed both the mountains and towers to make this film. Life has now settled down to the routine of operation. The winter footfall is well cushioned by a 15-foot depth of snow. A weather observation station is manned all year round on Kildella Pass. The nearest aluminum tower carries some of the equipment. The grandeur of the winter mountain scenery is only too often obscured by low cloud and flying snow. A door had been provided in the diagonal leg, in addition to the manhole at the base of each leg, so that the tower can be climbed when the snow is deep. Ladders permanently fitted inside the legs allow the whole tower to be inspected from inside. Furthermore, the tower is safe to climb with the line under power because the man does not encroach on the conductor clearance limits. Handrails are left on this cross arm because it doubles as part of the weather station. The towers are well suited to duty in wind-swept mountains. Their streamlined shape resists gales and heavy snow. The flat top gives a good footing for line maintenance, and in bad weather, trap doors allow access to the inside of a cross arm, from which insulators and their anchorages can be inspected at close range. The structure is safe from accumulations of rime. Aluminum remains tough in the Arctic cold. The aluminum conductor EMU is capable of carrying enough electricity to supply all the power needs of a city larger than Chicago. The power is transmitted at 300,000 volts. Simple to build in difficult places, light to transport, tough in cold weather. Aluminum towers are a strong link in the power line to Kitimat.
Spring 1951. The Valley of the Camano. Alcan crews had started construction on the aluminum project in British Columbia. 800 square miles of unused wilderness awakened out of the silence of time. Men began to gouge roads, build camp cities, and blast access tunnels, preparing the ground for hydroelectric development to provide the tremendous electric power needed in the manufacture of aluminum. Power that would maintain Canada's place in the world as a producer of aluminum. Thousands of engineers and construction men, billions of dollars worth of equipment moved into the area. To establish this new industry in British Columbia, it was planned to dam the Nechako River and form the essential reservoir in the tributary lake area. Then, 120 miles to the west at the end of Tatsa Lake, tunnels would be driven through the granite of a mountain range to channel the reservoir waters into the Valley of the Camano. where a great underground powerhouse would utilize the falling waters to create electrical energy. From here, a transmission line was planned to carry the new power 50 miles over the rugged terrain to Kitimat, the location for the new plant and town site to be one day the western center of Canadian aluminum. Access into a project of this scope is often difficult. On the Alcan project, every mile of road was a hard-won battle with nature. Several hundred miles of access roads were built to open the wilderness. In from Burns Lake, 120 miles of highway were built to meet a barge service on Tatsa that linked the tunnel inlet with civilization. And further east, another road was pushed down from Vanderhoof to the Grand Canyon of the Nechako, where construction on the new dam was underway. Early in 1951, giant machines were laying bare the foundation for the dam. Unused waters of the Nechako River would be harnessed to serve the needs of Canadians. First, a tunnel was to be blasted to divert the course of the river and allow engineers to get down into the canyon river bed. A few months later, as winter had settled down upon the canyon, the tunnel was completed. Engineers devoted their full attention to the temporary diversion of the river through this new underground course. At this time of the year, the river was at its lowest level, but still the swift current obstructed the building of a coffer dam. Thousands of tons of rock and dirt were dumped between the steep walls into the gap of the canyon. As the gorge narrowed, the current increased. Trucks kept on with the fill, and finally their objective was accomplished. On October 24th, 1951, a well-placed charge tore out the narrow barrier of rock over the mouth of the diversion tunnel. The river flowed through its new channel. Engineers had won the first round in their battle to stop the river. Through early spring of 1952, an examination and tests in the old riverbed revealed a foundation of solid rock. Hard rock men scoured the canyon walls and riverbed. Thousands of holes were drilled deep into the bedrock, and cement was forced in under high pressure. Every crack, every joint in the rock was filled to produce a solid, impervious foundation so that contractors could build the massive structure of the dam. Meanwhile, in the lake area, 60 miles to the west, other crews faced problems of their own. A barge service was to be established to carry men and supplies up and down Tatsa Lake. These barges, built in Vancouver, were shipped by railway and road and assembled in the lake area. Now the problem was to get them up the narrow Tatsa River and into their permanent place of service on Tatsa Lake. Treacherous currents of this unknown stream threatened disaster. Shoals, hidden rocks lurked at every turn. It took 5 days of fierce struggle to gain the quiet waters of Tatsa Lake. With the barges in service, the wilderness camp at the base of the mountain soon grew into a small city. At this site, the tunnel had been driven into the face of the mountain, and deep underground, hard rock miners were blasting their way toward Camano. It was going to take time to drive a 10-mile tunnel through a mountain range. As work in the tunnel progressed, camp facilities expanded to include many of the comforts of city life. In the sunlight above ground, miners' families found life in this mountain wonderland a pleasant experience. And school was worth attending, even if it was only to have fun at recess. Winter at Tatsa brought deep snow. But in this city of machines, snow was a minor problem. Underground on the tunnel job, seasons are all the same. And a steady stream of loaded mining cars coming out to the surface showed that miners were getting on with their job. At times during winter, because of the deep snow, the only contact with the outside was by air. Planes maintained the best possible schedules carrying men and supplies between Tatsa and the main camp at Camano. Here in the valley of the Camano River, Alcan Construction crews had also put their mark upon the wilderness. A wide cut cleared out of the bush of the steep mountainside marked the access route to the tunnel outlets. And below, at the base of the mountain, another camp city spread out over the valley floor. But here, as at Tatsa, the real story was underground. Inside the mountain, miners were carving a network of tunnels and excavating a powerhouse for the production of electrical power. 1,600 feet up the mountain, an entrance had been driven into the slope, and farther up at the 2,600-foot level, another passage led into the main power tunnel. Serving the needs of miners at these upper levels was a problem in vertical transport, adequately solved by the installation of an aerial tramway. Capable of carrying large tractors to the mountaintop, this represented another heavy investment in access equipment. At the top of the tramway run, 2,600 feet above the Camano Valley, a railway ran along a narrow ledge and vanished underground into the main power tunnel. Deep inside the mountain, miners blasted the headings forward in record-breaking drive. In one day, one of the 4 tunnel headings was driven forward a distance of 61 feet, a world's record, and an achievement that pointed clearly to superior organization and the closest teamwork. Early in 1952, a steamer docked at the Camano Deep-Sea Wharf, and a delegation of prominent businessmen, sponsored by the Vancouver Board of Trade, came ashore for a tour of the project. These men, taking pride in Canadian accomplishment, were naturally interested to see how Alcan was progressing with a project of such immensity. Deep in the mountain at Camano, a cavern to be ultimately 1,142 feet long was being excavated to form the underground powerhouse. In the darkness, laymen watched as miners removed the blasted rock from the powerhouse cavern. On the surface, the quiet mountainside belied the fever of drilling that shook its interior. Underground, an excavation large enough to hold the liner Queen Elizabeth and a complex series of tail race and penstock tunnels were being excavated. Miners who worked in this underground maze, whose efforts broke world records in driving of power tunnels, were pleased with their home in the valley. The camp at Camano provided many modern conveniences for the men and women engaged in this project. In rugged coastal British Columbia, supply is a major problem. On the transmission line, helicopters were used to fly men and material into the camps scattered along the route. This transmission line will carry the tremendous power up over mile-high Kildala Pass and onward to the plant site of Kitimat. Its aluminum conductor cables, 2 1/4 inches in diameter, will be the largest ever used for overhead power transmission. Alcan top executives and engineers made close personal inspections, for this transmission line is regarded as a Canadian achievement, one of the engineering feats of the project. Rugged terrain for transmission. Nevertheless, in time, 1.5 million horsepower will be dispatched over this barren pass to make aluminum in the smelter at Kitimat. Sprawling over the delta of a 70-mile inlet, Kitimat too reverberates with the roar of powerful machines. Soon, its deep-sea harbor will give space to ships from world ports with cargoes of raw materials to make aluminum. Today, an hydraulic dredge is taking silt from the bottom and spreading it over the low-lying delta with the double purpose of deepening and filling. Fill is no problem at Kitimat. 3 miles from the construction site, a natural mountain of sand and gravel rises out of the river valley. Giant trucks carrying 30 tons in a single load roar over the roads day and night, hauling this material to the site. Here, where in time the great buildings of the smelter will rise, carpenters work over the forms, and 24 hours a day, massive trucks keep a steady stream of concrete pouring into the mold. Spread over a total of 100 acres, the first stage of the Kitimat smelter will mean a new way of life for thousands of Canadian men and women employed in the production of aluminum. That production will reach over 500,000 tons yearly with the project's ultimate completion. The young city of Kitimat will take its place in this group of western communities and make an important contribution to the economic development of the area. Today, overlooking the site of the new aluminum plant, A camp city feeds and houses over 1,400 construction workers. This modern cafeteria is the largest dining hall on the project. But feeding 600 men at a time is a project all in itself. And the stampedes that shake its frame pay regular tribute to the excellent fare. To block the Nechaco River, the fill for the Kenny Dam required the blasting and trucking of millions of tons of rock. The endless stream of trucks that did the job worked between the quarries and the dam without let up either day or night for 5 solid months. With the possibility of an early winter, pressure was on to reach a stage where control gates could be closed and water storage commenced. Every level of this man-made mountain swarmed with machinery. Man did the thinking, provided direction, acted as the nerve center of operations, but machines did the heavy work. This dam, when completed, measured 300 feet in height from the old riverbed, a quarter mile wide at its base, and 1,500 feet along the crest line. A veritable man-made mountain. By early October in 1952, and right on schedule, construction engineers on the Kenny Dam announced that the time had come to start the storage of water. While it was conducted in a routine manner by men on the job, the closing of these gates would signify the achievement of an important stride in this project to make aluminum in British Columbia. On October 8, 1952, a busy crew assembled around the gate. This was the day. Without fanfare or ceremony, the great concrete slabs lowered slowly into place, cutting the Nechaco and turning its waters into useful surface. Tractors lost no time in pushing the fill in to complete the closing. And with this, the short service of the diversion tunnel came to an abrupt and permanent end. A plug of solid concrete was poured into the tunnel behind the gates, sealing them forever against the frailties of man and the ravages of time. Slowly the river rose. Inch by inch it began to creep across the toe of the new dam. Waters that had flowed unchecked through centuries now began to conserve energy for a mighty enterprise 150 miles to the west at Kitimat. The first major objective in British Columbia's Alcan project had been achieved, but still the work goes on. Completion of the Kenny Dam struck a resounding chord in the prelude to Kitimat, echoed across this land of the giants, to the intake at Tatsa, into tunnels at Kamano, all over the vast project, to the day when waters will surge through a mountain and their power will flash over the pass to a grand finale in the smelter at Kitimat. Across this great terrain, Canadians are putting to use the power of water to start a new British Columbia industry.
to make an essential and expanding product. Aluminum, bearing the well-known mark Alcan, made in Canada.
The development of British Columbia as an industrial province is a great story of man's achievements against the forces of nature. It began when British Columbia was an unsettled wilderness of rock and forest, studded with emerald lakes, scored with the courses of rampant waters, such and brutal land that held out with all its forces against the inevitable invasion of man. First of these invaders was Sir Alexander Mackenzie, whose venture through their granite wilderness to the Pacific Ocean is an epic of Canadian history. And later came the adventurers, lured on by the lust for easy gold in the Cariboo. Many succeeded, while countless others were driven back. But news of wealth more lasting than gold gradually carried to the outside world, and hardy pioneers crossed along the rugged coastline. In 1,000 inlets from Alaska to the Straits of Juan de Fuca, fishing fleets add their shimmering contribution to the wealth of the province. And deep in the heart of mountains, where minerals lie in hiding, BC miners blast still other treasures from the rock. Nor must we overlook the men of the soil, pioneers and sons of pioneers, who have sunk their plows in the yielding earth, rolling back the brush and swamps of stubborn valleys to reach still another great reward. And so it has been that in less than a century, these four basic industries have developed from humble beginnings to become the economic mainstay of British Columbia, an economy based on the natural wealth of the land and upon the pioneer spirit of its people. With this progress through the years, cities grew and people came, attracted from other parts of the world to this young and vital West. With this growth came the development of other industries to serve and maintain the growing civilization. Industries to manufacture finished products from the basic materials of the earth. And the new industry needed power. So man again harnessed nature, and early in the century, and as it turned the wheels of industry at an ever-increasing speed, far-sighted governmental leaders came to focus on best water reserves in the unsettled areas far in the hinterlands, and to recognize the possibilities of these reserves as the nucleus of other great manufacturing centers. As early as the 20s, surveys were started to determine the extent of this water power. A program got underway to induce manufacturers to the province. But manufacturers who need great water power resources were not easily found. So time passed. Circumstance intervened. The waters of the hinterland continued their wasteful course to the sea. But faith of mankind is enduring. Behind gray stone walls in Victoria, there still clung the dogged conviction that somewhere, somehow, there must be found a use for this power. The search continued with the years, and a time came when information was forwarded to the Aluminum Company of Canada, soliciting the company's interest in British Columbia. This was received with interest, but the company was starting construction of the great Shipshaw plant in Quebec, a project that promised adequate power for aluminum needs at that time. As yet the world had not accepted aluminum at its full worth, but that acceptance came all too suddenly, with an emergent demand on all the free nations of the world, war, and with it the demand for aluminum. The vast production resources of the company in eastern Canada were thrown into the struggle. Plants at Arvida, Ile-Maline, Latuque, Beauharnois, and Shawinigan Falls were geared up to 24-hour operation in turning out the products of conflict. Other plants at Kingston, Etobicoke, Wakefield, and Toronto likewise were pressed to capacity. And Canadian aluminum made its own important contribution to final victory. During the emergency, the company had devised methods of reducing production costs. And as peace returned, there came from the war-torn world an increased demand for the products of reconstruction. Among them, aluminum in all its forms. Electrical equipment, household utensils, building materials created such a demand for ingot production that the company was obliged to look forward again. Expansion was indicated, but where exactly? Canada, South America, Africa, New Zealand, or Borneo? It would seem that destiny must have prompted a second approach by the British Columbia government to the aluminum company at that specific time. For negotiations developed quickly, and the government sent Mr. Kenny, Minister of Lands, and his deputy, Mr. George Melrose, to make a personal inspection of what the company had accomplished in the province of Quebec. In the course of their trip, they visited the model town site and the great plant at Arvida and studied the manufacture of aluminum. With keen interest, they viewed the clean, modern community of friendly, happy people. Here was the home of an industry, demonstrating beyond doubt its responsibility and capacity for healthy progress. Here was space for gracious living. They toured the company docks at Port Alfred, stirred by information that the port handles an aggregate annual total of over 2.5 million tons. They examined the company's power development along the Saguenay. 2 million horsepower harnessed for aluminum production. Here was major industry. To the two Westerners, 40 long years of search for such an industry seemed to climax at this moment. This was their time for action, and action followed. In the spring of 1948, Alcan representatives, on invitation of the government, visited British Columbia, and what they saw and heard here impressed them. They needed tremendous water power. They needed a sheltered harbor with access to shipping routes. They needed a town site for 50,000 people. Above all, they needed a cooperative government and a sympathetic people. British Columbia gave promise of all. It was subsequently agreed that the company would spend $1 million in a survey of the wild areas of northern BC. But these men were not sightseeing. They were, in essence, pioneering a new industry. This was a preliminary examination covering two prospective areas. The first one, known as the Chilco area, centers about a point 150 miles due north of the capital city of Victoria. This was duly examined and passed up for various reasons. The second, about 350 miles north of Victoria, is called the Nechako-Kitimat area. In close-up, we get some idea of this area and of the lake chains which flow easterly into the Nechako River. Also an impression of the rugged nature of the Pacific coastline. Studying these areas reassured Alcan engineers that government reports were accurate. Besides finding water reserves adequate for efficient aluminum production, a suitable plant site was located at Tidewater. The prospect looked good. More detailed examination was conducted during the summer along the inland water courses. Once again, survey data provided by the BC Government Department of Land proved extremely helpful. At Kitimat, engineers found the forsaken wilderness. For these men had prospected before, this was nothing new. One thing was certain, adequate space for a plant site with wharf facilities and a town site were there. And these men knew that what had been done before in a quiet valley in Quebec could be done again in the wasteland of the Kitimat. On the strength of this early examination, Alcan set up survey offices in Vancouver. Contracts were let to the BC International Engineering Company for general engineering and to other British Columbia companies for field work, transportation, and other services. And in June of 1949, the field survey got underway. The watershed area is a glacial plain, generally level, but rising sharply to high mountain crests at the western end. Two main lake chains converge into the Nechako River, draining them eastward. The general proposals for development may be easily followed. By damming the Nechako near its source, these lake basins would fill in time to form a continuous reservoir, as shown in the darkened areas. Now let's look to the west. A second dam across the Nanika River would likewise impound the waters in this lesser area. These, in turn, would be drained through a 3-mile tunnel into the main reservoir. The waters of the entire area would thus be available for hydroelectric use. To put them into service, 2 10-mile tunnels would be driven through the western mountain range from the end of Tapsa Lake, and the water dropped 2,600 feet through penstalks within the mountain to the valley of the Kamano River. Here the great powerhouse would be located in the rock, and from here a transmission line would convey the electrical energy overland to the proposed plant and town site at Kitimat. Based on this general plan, the survey proceeded. But engineers were faced with numerous alternatives, and so every avenue of thought had to be investigated before any conclusions could be drawn. For instance, in the reservoir alone, there were 27 points for investigation. Many of these canceled themselves out on paper, but others required on-the-spot investigations and field crews spread out all over the vast area. At this time, the focal spot of the survey came to rest on finding a dam site on the Nechako River. The best location appeared to be this one, about 4 miles downstream from Natalcos Lake and called the Butte site. Here camp was established for 40 men. The survey was now getting down to practical proving of drawing board theory. Surveyors went into action first, establishing levels and marking locations for test holes. And then drill crews moved in to test the rock conditions on either side of the river. One crew started work near the water at the foot of the butte. Inside of 2 days, cores showed sufficient promise of good foundations to raise hopes, but only for the moment. The drill on the south bank told a different story. Drillers sank their diamonds 10, 50, 100 feet, and 3 weeks later, 170 feet into the earth. But cores showed nothing but gravel. Where was bedrock? So, consulted with field engineers on the characteristics of the site. They agreed that while still a technical possibility, the cost of a dam at that site would be prohibitive. An alternative site must be found. And so, project number 1 had drawn a costly blank. Nature had won the first round on the Nechako. Meanwhile, 150 miles to the west, at the end of Douglas Channel, a party of surveyors had invaded the solitude of Kitimat. This inlet is located about 40 miles due south of the town of Paris, which is on the main line of the CNR between Prince Rupert and Edmonton. In this lonely inlet, surveyors of Swan Roads and Wooster Company were now engaged in mapping the area for plant and town sites and conducting another survey on the action of the tides and of the river. Weather recording was likewise being done. Working in all kinds of weather, living in rough tents, out of contact with civilization for endless days, surveyors toiled on, spurred by the knowledge that they were pioneering a new industry. Down in Vancouver, the information they supplied was gradually being compiled, and the thought stages of the project were taking more concrete form. This artist's sketch conveys the thoughts that were developing for the future of Kitimat Valley. The plant would likely be located in the Delta area on the deep side of Kitimat Arm. The town site on the elevated ground in the upper valley across the river. Like Arvida, this is intended to be a model town site, the last word in community planning, laid out for an eventual population of 50,000 people. The plant, to be developed in progressive stages, would be located for access to wharfage and designed for an eventual output of 1,100,000,000 pounds of aluminum ingot per year. During this time, a survey had been conducted in the area of Nanica Lake and along the route of the tunnels. The party from there now returned to the outside world with final data. In due course, this found its way to the engineering office. The Nanica site became the subject of many discussions, for numerous alternatives were involved. The most favored arrangement at the time was committed to drawings for the purposes of costing. This artist's perspective gives an idea of the location on Nanica River. The foundation proved up to be sound, solid rock. Stripped of overburden, it's expected to look something like this and is considered by engineers to be a good location. To facilitate construction, a tunnel 25 feet in diameter would be driven to divert the water of the river, and 2 copper dams would be constructed to provide a dry riverbed for building of the dam itself. This would be of rock-filled and clay core construction and measure 150 feet in height from the riverbed and have a crest length of 800 feet, nearly the length of 2 city blocks. In addition to this, a spillway was to be blasted into the left bank to provide against flash flooding and to supply rock for the dam. When completed, the dam would impound 400,000 acre-feet of usable water to be drawn off at the upper end of Nanica Lake and discharged through the 3-mile tunnel down into Tatsa Lake. At this same time, data on the route of the Tatsa-Camano tunnels was taking practical shape on paper. This sketch shows the tunnel route from the Camano end with some impression of the rugged terrain of the area. Let's cut away the mountains and take a look at the detail. From their portals on Tatsa Lake, 10 miles away, the tunnels would follow a course through solid rock to a point 2,600 feet above the Camano River, here to connect with Penstock, also tunneled through the rock. From this point, the water would drop to a battery of turbine generators in a powerhouse below. This powerhouse would also be contained in a man-made cavern deep within the mountain rock. From here, the electrical energy would be transmitted up the Camano Valley and overland to Kitimat. So the survey progressed, and a number of sites in the system were proven up. The plant site, one of the major dam sites, and 2 tunnels had been investigated, while a number of lesser dikes and dams had likewise been proven to a satisfactory degree. This was indeed encouraging, but when a company is contemplating development in hundreds of millions, no point can be left to chance. There remains still much to be done. All too soon, the icy hand of winter gripped the Northland, and except for the study of weather and its effect on water conditions, field work had come to an end. But the hydrometric survey was equally important as any phase of the job, and throughout the winter, engineers maintained a constant round of visits to points all over the area. Special equipment had been located at strategic points to measure the river flow beneath the ice. Snow in winter lies frozen on the mountains, and water levels drop. It was therefore necessary to determine what the winter runoff would contribute to the reservoir for power production. These delicate instruments were used to automatically record water levels under the ice. In the rivers where ice did not form, another system was used to measure the runoff. Data was gradually accumulated through the constant use of these instruments, and by cross-checking results with government weather reports, some reasonably accurate figures were compiled to justify the assumption that winter, while always a problem, would not prove detrimental to the project. The 1950 survey on the Nechako River took place at a new site in the canyon, about 11 miles downriver from the old Butte site. By the late spring, the new camp had been established. Surveyors, drill crews, and engineers again took up the challenge of the river, this time doubly determined to find a way to harness its latent power before winter again set in. Surveyors who had toiled themselves to a standstill at the old Butte site now took their sights and drove their stakes with determination into the new soil. It had been decided in previous studies that a dam across the narrowest part of the gorge would be best located for final results, and surveys were carried out accordingly. Meanwhile, down the 75-mile waterway from Utsa Landing, drilling equipment began to arrive. There was little in the way of formal greeting. By this time, the long run had become daily routine. Unloading got underway almost before the boat touched shore. After the drill had been assembled and mounted on skids, yarding it 3 miles into the canyon was in itself no small job, even for these experienced men of the Boyles Brothers Company. Up to this time, the survey had been concentrated on the south side of the river, but now surveyors had to cross to the north. This was still another challenge to the experience of BC bushmen. And as this need for ingenuity came, they were prepared. The canyon had to be crossed to conduct a survey. They would do it. And here was their answer. Not what you call a joyride, but safe enough if you have the self-confidence and strength to get yourself across. Close on the heels of surveyors, drilling got underway. Men who spend their lives pushing holes into the earth get to be fatalists in a way, for nature plays funny tricks. A drill may go through solid rock for 50 feet and then strike nothing but clay for the next 100. The only proof of what lies beneath is what comes out with the drill. However, engineers in examining the cores of first holes were satisfied, and later drilling, continued across the site throughout the summer, added up to a foundation of solid rock, an ideal dam site. By late summer of 1950, the field survey of the Nechako Canyon had been completed. This sketch, developed from engineering drawings, illustrates the general plan for the dam. First, a tunnel 25 feet in diameter will be sunk through the rock around the canyon area, and a cofferdam built just below the portal will divert the flow of the river through the tunnel, making the canyon accessible for construction of the dam itself. This would be a rock-filled dam with clay core seals and would measure 280 feet in height and 1,800 feet long. In anticipation of its completion, the diversion tunnel would be blocked before the water rose, allowing the water to flood the valleys above. It is estimated that with usage, the reservoir will require a period of 4 years to fill to maximum elevation. While much of the transportation into the lakes was carried on by plane, heavy equipment was hauled in by road from Burns Lake on the CNR and down to Utsa Landing. Utsa Landing is the access point into the lake area and one of 3 small adjacent communities along Utsa Lake shore, the other 2 being Wisteria and Marilla. Early in the survey, Alcan engineers realized with concern that parts of these communities were in the flood area, and that some of the friendly people would in time be obliged to leave their homesteads if, as, and when flooding should take place. In Alcan offices, an intensive study has since been conducted. Relief maps have been made to determine the effects of flooding. The waters of Utsa Lake are expected to rise about 140 feet. But development of the project would, in any event, require 2 or 3 years to reach a stage where inundation would affect the settlers. In the meantime, it may be expected that a full and satisfactory relocation of these people would take place. In time, the attention of engineers turned to the transmission line, the vital link of shining aluminum cable that would convey the tremendous power from the generators to the site of the plant at Kitimat. Engineers flying over the area viewed with some apprehension the forbidding barrier. 50 miles of rocky, mountainous, snow-clad wilderness. The big question was not could they build the line, but rather could any line be built to withstand the rigors of the elements, rock slides, ice, snow, and sub-zero temperatures. In engineering offices, data was assembled and studied intently. But figures on weather and topography produced nothing but a big question mark. Discussions all led to one conclusion. They would have to erect towers and string cable to make an on-the-spot test. Late in 1950, a chartered cruiser anchored at Kildella Arm near Kitimat. The tower members, prepared in Vancouver, were about to be carried into the mountain wilderness, there to be erected on the 5,000-foot summit and left to withstand the long, dark winter. A crew of weather observers were likewise giving up the comforts of civilization to spend the winter in snowbound cabins. Before them in the distance lay their objective, the forbidding barrier across the treacherous route of the power line. In a lonely tidewater camp, men had been observing. To keep ahead of bad weather, haste was imperative, and trip after trip was made without a pause until men and equipment had been safely carried to the site. And here they were, 5,000 feet above the sea. Looking from the summit, one could see the rugged route to Camano Bay. Up this route, 3 surveyors were now heading, examining the line on foot. For the men on the summit, the good weather held. The test towers began to take shape, but there was no telling when a squall would develop, and an open mountaintop is no place to weather out a storm. Anchor bolts had to be grouted deep into the rock. There was little time for conversation, but no doubt some views were exchanged as to when the transmission line crew would reach the summit. And on the 3rd day they arrived, crossing the glacier higher up to avoid quick disaster in a slide to the valley below. 25 miles of grueling climb lay behind them, and now they faced the descent. Another 25 miles of still tougher country, crevassed by streams from the ice, blocked by cliffs and barriers of broken rock. What lay in the deep shadows of the Camano they were determined to find out, so that a power line could be built. But for the men on the structure, there was no time for visiting. A cloud condition might develop and remain for weeks. Flying out would be impossible, and these men had no wish to cover the same ground as the survey crew. 5 days after arrival, both towers were erected and the short test cable strung. Only a few hours more of adjusting and testing, and the delicate instruments could be installed. Instruments that would automatically record the winter ice loading on the cable. This would provide the vital data needed by engineers in working out wind pressures, spacing of spans, and 101 other contingencies in the designing of a permanent power line. The next day, these instruments arrived, and 2 days later were installed, ready for their long winter service. After 7 days of eating their own cooking and shivering through the glacial night, engineers were glad to board their aluminum Dragonfly and turn over the desolation of the mountaintop once again to nature. Late in November of 1950, Mr. McNeely Dubose, Vice President of the Aluminum Company of Canada, visited Mr. Kenny in Victoria. From time to time, progress information on the survey had been forwarded to the Minister of Lands, but until now, no definite statement had been made by the company because of uncertainties still existing in the field. At the time of this meeting, however, Mr. Dubose was pleased to announce that a review of field data proved beyond doubt that the production of aluminum in British Columbia was an economic possibility. Negotiations were resumed, and on January 2nd, 1951, papers carried the news that the minister had signed an agreement granting the aluminum company permission to go ahead and develop the Nechako-Kitimat area. To the man on the street, this may have signified immediate action by the company to start spending hundreds of millions of dollars in development. But businesses spending hundreds of millions do so with caution. From the driving of its first survey stake, the industry in Quebec took 30 years of cautious, progressive endeavor to reach its present world position in the production of aluminum. Based on this experience, the development in British Columbia has been planned to take place in 3 progressive stages, governed by growing requirements for the product. Vital defense programs may, however, require full development of the area immediately. Against this possibility, the company is spending large sums of money, and now in early months of '51 is building access roads into the Camano Valley and freighting quantities of equipment and supplies into the Nechako and other parts of the area. As the needs for aluminum develop, Alcan is bending every effort to be met with a British Columbia product, a product that requires nothing to land but the power of wasting water. Soon now, these rampant forces of the Northland may meet their destiny in final service time. A service that will mean larger payrolls and still greater prosperity for the pioneer people of British Columbia.
Of this math project and its importance to us in North America and to everyone in the free world. It is a story of men. Men of Morrison, Knudsen, Mannix. It's also a story of machines. Machines from hundreds of the United States and Canada. Inevitably, it becomes the story of the basic machines of construction. The big red crawler tractors. Because more of them were at work here than have ever been assembled on almost any single project in the world. And because they are doing the toughest jobs imaginable, they become the mechanical heroes of this epic struggle against the elements. The picture was made possible by International Harvester Company, manufacturers of the big red crawlers, as visual evidence of their amazing ability to lick the roughest construction jobs in existence. I mention this now because no attempt is made to point out these important facts in the picture itself. So this is a story of men and machines and the wonderful work they are doing in the wilderness of central British Columbia. Back of this is the high purpose of a better way of life for all of us and greater security for the freedom-loving peoples of our Western world. It is with great pride, as one Canadian-born, that I will help to bring you Harvester's wonderful story of the construction of the Alcan project, the picture called Man with 1,000 Hands. Man has always been a builder, seeking to conquer waters and lands of his earth for the good of those who follow him on its surface. Not all regions of the earth have bowed to his will. To the north of Vancouver, up the still fjords, south of the Yukon and west of the Fraser, guarded from man by the granite and ice and winds of the coastal mountains, lies such an unconquered region. It is a region of great resources long held from use, of treasures long locked away from productivity. A region guarded by distances and shielded by storms. A wilderness set off from the modern perimeter towns by its challenging terrain. Once nature's challenges were met by throwing great masses of men against them. But against this challenge, the armies which had cleared the forests and spanned the continents and brought the wastelands into bloom were of no avail. For men could enter here only in small numbers. And so for a long time the region, its resources little used and wasting. Now, strange things are happening in the wilderness. Strange creatures are prowling the land. Giants with muscles of metal and blood of diesel fuel, whose steel claws rip away the distances and tear at the terrain, snorting defiance at the storms and chasms. And giants are working in the land. Giants who steal sinews, bows, and strain, that man and his children may live in greater comfort and safety and abundance. Giants of metal and power. Man's new race of slaves. These giants labor in a region touched only lightly by the Iron Age and the Bronze. To move it at one step into the newest of the eras, the age of the light metals, of the metal aluminum. Aluminum is drawn from an inexhaustible source, the clay bauxite. Bauxite reduced to alumina and smelted by power to a metal which is light and strong, resistant to corrosion, useful in peace, vital in war. A metal which can be rolled like steel, extruded like plastic, and drawn like copper. A metal whose lightness releases energy to do things once thought impossible. The alumina is reduced by power, electric power. Power in quantities undreamed of not many years ago. Power enough to light a city or run a railroad. And the power is best made of water, falling water, which turns the wheels of turbines in its fall. If aluminum is to be plentiful and cheap, the power must be cheap. Men must search the world for a place where an inexhaustible supply of water falls continuously from a great height. Here in north-central British Columbia, 400 miles north of Vancouver, is such a place. Here in the shadow of the Yukon, the eternal snows promise inexhaustible water. For 1,000,000 years, the cycle of nature has replenished the water. The snows come, the rains fall, the glaciers freeze and melt, and the rivers flow out, and the water falls again. And the water is high in the mountains. Here is a model of the region. The water is high in the mountains, and near it to the west is an ocean channel where ships can bring the alumina to the power. But the water is separated from the ocean by a mountain wall. Can they together? The water gathers in the chain of lakes, 150 miles of lakes, like a vast broad tub, and it drains out of the tub to the east through the river called the Chaco. Here the men and the machines will plug the drain with a great dam. But they will not use the water here, for the water now flows, and it must be turned to flow west toward the channel where ships will bring the alumina. The dam will block the gorge, and the lakes will begin to fill, rising higher and higher against the mountain wall which for 1,000,000 years has barred any westward flow. And here the men and their machines will tip the tub the other way, a tunnel 10 miles long. And at the western end of the tunnel, they will turn the water downward, through pipes called penstocks in the very heart of the mountain, in a fall 16 times the drop of Niagara, to the turbines which will convert the fall into electric energy. But if the water falls inside the mountain, how can the men bring it out to turn the turbines? They will put the powerhouse inside the mountain. At the place called Camano, their machines will gouge out a vast cavern in the bowels of the mountain itself. A cavern the length of 2 city blocks and the height of a 10-story building, making power enough for half a state or province. But the power has no room to work here where it is made. There is no level ground for a smelter and the people to run it. So the men will build a line of towers, the heaviest transmission line ever planned, to carry the energy 50 miles up over the eternal ice and winds of the Kildala Pass and down to the delta of the Kitimat River. Here, the only such place in many miles, is level ground, adjacent to the ocean channel where ships from faraway Jamaica can bring the alumina to the power. Enough level ground for a city which will be called Kitimat. This then is the project. The new city in the wilderness, the transmission line over the glaciers, the powerhouse inside the mountain, the tunnel river through the mountain barrier, and the watershed the size of the state of Connecticut, reversed by a man-made dam. Any one of these 5 projects would be a vast undertaking in itself alone. That has not before been attempted. Not only for himself, but for his new race of giants. Now he can challenge the unconquered regions of the earth on even terms. With his own 2 hands, a man can do just so much. To do more, he must use his mind. The hands of the mind are machines. The man with a machine has 1,000 hands. Like the machines, the projects which machines will build take shape first in the minds of men. Men who think and decide. Men who plan the work, and men who carry out the plans. The projects come into physical being through the minds of the men who direct the machines, and through the minds and hands of the men who come into the wilderness to run them. To block the eastward flow of the Nechako, the men and their machines will drop a mountain into its gorge. To move the mountain, they must first take it apart. And so they have undermined it with a network of tunnels, hundreds of feet deep. And in the tunnels, they have piled dynamite. Dynamite in whole boxes, 168 tons of it. The roads have been blocked off since dawn. The mountain is waiting. Ten men use 20 hands to scale down the loose rock, while one man in a machine scoops tons of rock. men work together, and the machines work together. Each machine does what it can do best, and together they make a team. The men have taken the mountain apart. Now they must move it to the river. And there is little time, for the dam must be closed before winter stops the work, or a year's water will be lost. The trucks roll a round trip every 12 minutes. A loaded truck dumps every 45 seconds. The machines have moved the mountain to the river. Now they must put the pieces back together in the shape of the dam. The river itself helps build the dam, which will block its course. 3,000 gallons of it every minute roar against the falling rock to shove and settle the broken mountain into a compact mass that will hold back 150 miles of lakes. The river is dammed by rock and clay. The body of the dam is rock. The impervious core which seals off the water is clay. The machines dig the clay from a pit above the dam, breaking it up and wetting it down so that it will pack into a solid mass. Machines work together. One machine makes ready for another. The big red crawlers spread the wet clay for the scoops to pick up on the run. In the days of the pick and shovel and dump carts, a man had to work 12 hours for his day's pay. Now his work is shorter and easier. But the machines let him turn out more work and make more money, and everybody gains. As the summer fades and the cold months come closer, a new load of clay rolls to the river every 30 seconds. The machines work together. Strop the clay, the crawlers spread it level, and the sheep's foot rollers compact it into a layer so firm that a cubic foot weighs almost as much as a man. 100 100 men work with their hands on the canyon wall, preparing for other men whose machines will gunite and grout the rock with concrete, forcing liquid cement grout 100 feet down into the rock to spread like a cloud through the pores and fissures, over which other men tamp the clay against the rock to make the impervious seal. Quarter of a mile across, 300 feet high above the riverbed, the dam must be sealed before winter stops the work. And so the work never stops. September. The men and the machines are winning, and the gates of the diversion tunnel can be closed. This year's water will not be wasted. In a few years, here, near the dam, the land will be covered as the deep storehouse of liquid power rises toward the western wall. The lakes will rise rather than spread, but soon boats may sail in smooth water 100 and more miles from the Chaco to the western mountains. Men and machines must have food and fuel and supplies. The logistics are those of an army fighting on 5 separate fronts. Before the jobs could start, the roads had to be driven through the wilderness, through swamps, through forest, over mountains and muskeg. 60 miles of road from the railhead to the dam, 104 miles to the head of navigation on the last lake of the chain, the lake which could carry supplies to the western mountain wall. Lakes called Itzuk, Tetachuk, and Antico, lakes called Intata and Utsa, and Tatsa, where waters rising here against the western wall. Beyond the storm-shrouded mountains lies the valley of the Camano, where the power will be made, 10 miles west and half a mile down. Through these mountains, the men and machines are drilling a river. The shore ahead will soon be the bed of the lake. Except for the gatehouse, which will control the flow into the tunnel, there will be nothing above the waters to show that man has passed this way. Here it is that the hard rock men will tip the tub the other way, driving the 10-mile tunnel which will carry the water from the lakes to Camano. This giant is a drilling rig called a jumbo. On its 4 levels, 16 drillers push hardened steel into the rock. 12 feet, 13 feet, 15 feet to a blast. The hard rock men go where the work is. One continent or another, there is little difference under the ground. The lights gleam yellow in the haze. The water drips shining down the jagged walls. And compressed air roars against the clang and hammer and scream of the drills. Drill, load, and shoot. That's hard rock. 2 hours to drill, an hour to load the holes with dynamite. load, shoot, and muck out the shot debris. The barmen are the two drillers who work on the top platform of the jumbo. If they should leave a chunk of rock hanging loose in the roof, it will be on their own heads. This machine is a mucker, a dragon eating a hole through the mountain, banging its jaws against the tunnel face as it hurls mouthfuls of shot rock back through its iron throat into the ore cars which will carry it away. Behind the mucker is the cherry picker, an ingenious giant whose clanking arms let the last become first. When the mucker has loaded the front car of the train pulls back, and the cherry picker hoists an empty car in the air so that the loaded cars can roll back under it. Down at the head of the train, thus avoiding a need for double track. The train rolls back into the mucker, and the work goes on. Drill and load, shoot and muck. The men and the machines are driving a river through the mountain. "10 miles west and half a mile down lies the valley of the Camano. The mountain blocks the way, and there is no road. But the men have a giant that builds its own road. The planes make a week's journey in minutes, riding up the thermals to gain altitude in the narrow valleys, flying not over the mountains, but in them and through them. Behind the granite battlements, beneath the sculptured white of the snowfields and the ribbed blue ice of the glaciers, the men are driving a river through a mountain. Above the valley floor, a camp clings to the mountain. Below the aluminum buildings is the west entrance to the tunnel, deep in which men are driving eastward to meet the men boring west. One day a shell of rock will fall, and the two gangs will look through a jagged opening into each other's faces. And neither will be surprised at being able to come together deep in the earth, accurate to the inch. Drill and load, shoot and muck. The men go in and the rock comes out. Here the water must turn downward on its plunge to the turbines. But even 12-inch armored steel penstocks would burst under this awful pressure. And so the men are making their penstocks out of the rock itself. They will plug the main tunnel a half mile in from the face and drill slanting tunnels downward through the very heart of the mountain to make a fall 16 times the drop of Niagara. This is where the water will plunge down inside them. The The path in the trees marks the track of another iron giant. It was thought impractical to blast a road up the steep cliffs to the tunnel portal, so they hung a road on cables. And on it, a skip the size of a yacht can transport 80 men or 20 tons of equipment. Camano is the central camp of the project. Here will be the power plant. To the left, the valley carries a road to a tidewater harbor and a seaplane base. To the right, it will lead the power line up into the mountain pass to Kitimat. If the water falls inside the mountain, how would it be brought outside to a powerhouse? And how would the men build a powerhouse strong enough to stand firm under 50 feet of snow, under the avalanches and rock slides from the frowning valley walls and the roaring spring floods of the river Camano? Like all great ideas, the engineers... Inside the mountain, at the bottom of the penstock tunnels, the machines muck out the power cavern. 2 city blocks long, 10 stories high, vast enough to enfold a cathedral in its rocky embrace. The men start at the roof and blast their way downward, shooting the floor and dozing the rock into holes, to fall through the mountain to the shovels and trucks which work on the bottom level. The men go in and the rock comes out the same tunnel from which soon a foaming torrent will burst on its way from the turbines to the river and thence to the sea. There to be picked up by the sun and fall again as snow and rain into the high lakes. Here in the swift northern rivers, the big red crawlers go fishing in business hours. Concrete to line the power cavern and the tunnels. Concrete to support the transmission line towers. Concrete must have gravel. And a few yards from the tunnel portal, nature washes gravel so bountifully that the crawlers need only to push it into the path of a tractor-powered dragline. On this project is gathered a concentration of heavy equipment probably greater than any outside of... The job uses 52 of the huge TD-24s alone. The crawlers go in, the gravel comes out. The same big red diesels that power the crawlers drive the gravel plant, and concrete will line the stomach of a mountain. Up the still fjords, into the mountains where the giants are at work, the men come from all over the world to run the machines. The men are building a shadow town. For when the turbines start to sing, town will vanish. There will only be a few houses here. But now the shadow is very much alive. Kept alive in the tradition of construction camps over the globe on pie for breakfast and steak for lunch. A few girls are here, as secretaries, clerks, and nurses. In this kind of country, the first rule of eating is to get full of food. This rule is universal. With his two hands, a man can do just so much. Soon this man may be doing it with one. To the north of Vancouver, in the shadow of the coastal mountains, the land is vast and the people are few. And sometimes they remember that they are a long way from home.
Dream time, sweet memory, my thoughts turning to home. Moonlight carries its spell, and moonbeams stories to tell, and moonlight is dream time, dream time, sweet memory.
Here in the north, the dark comes late and the dawn comes early, and the giants stir in the morning fog. The power must go where the work is. Here, where the power is made, there is no level land for a smelter, and so the power must go where the work is. Each tower is designed separately for its own load and position, and the cables will be thick through as a man's arm, woven of 100 aluminum strands, woven to carry 5 inches of ice, woven to carry 40 pounds of ice to the foot, swinging in long spans over the rocks between the towers, swinging 3,000 feet in a single span over the ribbed blue ice of a glacier. The line starts near sea level, here in the valley of the Camano, and in a few miles it climbs to the clouds. In the beginning, there was no road. And even now, the road is steep and slow. And so again, the men call on their giant that carves a road with its wings. Seen through the pulsing heartbeat of a helicopter, the ground of Camano looks white, for this is glacier country. High in the mountains, the ice has been grinding the rock to fine powder, and the powder colors the green-blue streams with milky white and leaves whiteness on the beds and banks. A few miles above the camp, the river goes north, and the road for the line leaves it to follow up the narrow cleft of Glacier Creek. Along the Camano, the line goes, and up the cleft of Glacier Creek, over tower locations whose only road is a helicopter landing platform and the lonely pole of a high line. Higher and higher the line will climb. Up the rocky cleft will climb the cables, thick through as a man's arm. Up the cleft of Glacier Creek, over the glaciers themselves, anchored deep against the gales which roar through the high pass, and down the green valley of the Kildala, 50 miles northwest from the turbines, a mile up and a mile down, the power goes to Kitimat. The light loads can go up the line by air, but the men need steel and cement and cable and machines. And so they are driving a road up the cliffs, a road that costs more than a modern superhighway, blasting a narrow shelf out of the sheer rock walls. Air compressors for the drillers, power units for the highliners. The heavy equipment goes up on timber skids. The timber skids are little changed from the days of the lumber crews. But now the power that pulls them is painted red and drunk from diesel fuel instead of hay. The road climbs 1,000 feet to the mile, climbs grades of 15 to 25% up where the air is thin and clear. The rock falls and the snow slides and the road goes out. And the men and the machines put it back, and the road keeps climbing. In the spring, there was no road here. The men were stopped 2 miles below the pass, and the tortured rock ahead was overlaid with 1/2 feet of snow. On May 14th, Albert Charon, a French-Canadian, and a helper named Bill Henry, took a TD-24 crawler out onto the vast upsloping snowfield. Early on May 17th, they reached the bottom of the narrow chute which pierced the final head wall. A helicopter dropped fuel, and the huge crawler began grinding its tracks up the almost vertical chute. From far below, the men watched. Suddenly, the snow gave way, and the big red crawler began to slide and spin, sledding 400 feet back down the snow cliff, when miraculously, its tracks piled up enough snow to stop the plunge. The next day, Charon and Henry started up again. On May 21st at 8 p.m., they leveled their tracks on the summit of the pass, and the Glacier Creek Road was licked. Along the Camano, up Glacier Creek, and over the pass goes the road for the line. The men start down the hanging valley at the Kildala. Drill it, shoot and muck. Shoot the holes and muck out the shot rock. The rock goes over the most beautiful dump, and the road goes down the Kildala. May fall, and it's hard hat country for the crawlers as well as the men. Over the pass and down the Kildala, the men and machines have gouged a shelf in the rock. It looks so easy after it is done, but it is not easy in the doing. Works from the top down. Another gang works from the bottom up. And when they meet, there will be a road for the line. Shoot and muck up in the rock, doze and fill down in the rainforest so that trucks can haul supplies for the line. And the power can go from Camano to Kitimat. The machine helps the men, and the men help the machine, anchoring its cable around a stump when the hill is steep so that the machine can pull itself up by its own tail. A machine needs a part. Radio to the base. The helicopters will have it here in an hour. Miles from a telephone line, a man is hurt. Radio for a doctor. The helicopters will fly him in. Hours from the base, a rock gang needs air hose. Radio for it. Camp 10 is short of fresh milk. Kitimat wants a charter plane. Radio for it. Thousands of men doing hundreds of jobs, spread out over 5,000 square miles of mountain and forest, are tied together by radio like a small-town party line. The job couldn't be done without radio. The radio saves days, the helicopter saves years. The big Sikorskis are the freight wagons, the little Bells are the Pony Express. From Camano to the Kildala Pass is 5 miles northwest and a mile up. Diesel fuel for the crawlers, fresh milk and meat for the high camps, maintenance for the machines, fast transportation for men in a hurry. On a clear day, the Bells make 55 round trips. In this wilderness once would have been laid out by men on the ground. Men floundering in the muskeg, cutting through the bush, stumbling through the swamps. Men pinned down by flooded streams, laboring up the rocks and over the snow, blinded by the thick forests and wasting days in dead-end clefts and canyons. This time the roads were laid out from the air. from helicopters flying from barges anchored in the fjords. The job couldn't have been done in that time without the copters. Man wants to go to Kitimat? Man will go to Kitimat. 50 miles away, the water falls inside a mountain, and the power comes from Camano to Kitimat. The way has been cleared through the forest. The road for the girders and cement and cable is coming down the Kildala, and soon the line will carry the power from the lakes to the smelter. The land is level here, the only level land in many miles, and near it is an ocean channel for a new deep-water port to serve the broad and fertile hinterland. The land is level. The land is unstable here near the shore, made of water and saturated sand and fallen trees, 1,000 generations of fallen trees, which must be stripped to the rock and replaced with good, hard gravel. A mountain of gravel, shovel by shovel, and truck by truck. Goes down now, and the foundations will be solid. And soon a smelter, 1.5 miles long and 0.5 mile wide, framed walled with thousands of tilt-up slabs and acres of aluminum siding, will provide the life force of a new city. A city which will start its life with more than 6,000 people and may grow to 50,000 as the abundant low-cost power draws other industries. Acre by acre, the ground is wiped clear like a giant drawing board, waiting for the structures of the unborn city to be sketched in, waiting for homes like those of another city brought forth in the wilderness by power and aluminum, for the people who will come into the new land and live and raise their children into a prospering land which once supported little more than the lumber crews and the fishermen. Kitimat will grow as its people want it to grow, by their enterprise and in their freedom. But now the homes are yet to be built, and so the work of clearing goes on. And all the trees that men will clear for their city are fewer than fall in the winter storm. The 10-ton steel ball holds the chain low on the trees, and the chain, pulled at each end by a plunging crawler, does a year's work in a week. To the north of Vancouver, guarded from man by the ice and granite of the coastal mountains, lies a region which once was unconquerable. Soon it will yield its treasures. But there are vast regions still unconquered, still with their treasures locked behind nature's barriers. Barriers which now may be breached by man's new race of giants. For a man's two hands can do just so much. To free himself from drudgery, he must use his mind. A man's hands could do just so much. To do more, he has used his mind. The hands of the mind are machines. The man with the machine has 1,000 hands. And he and his children better life.
Low-cost power and economical water transportation are vital to its competitive position. Since the turn of the century, Canada's aluminum industry has been centered in the province of Quebec. What then influenced the company to expand westward, to invest more than $400 million establishing an aluminum industry in what was then a wilderness of coastal British Columbia? Here was a region of high mountains rising abruptly from the ocean, peaks and crags thrusting upwards, stripping the moisture-laden winds. And beyond the mountains, a short distance to the east, a high plateau where rain and melting snow gathered in a vast lake area, half a mile above the sea. Here was an area with a hydroelectric potential of millions of horsepower. In 1948, man came to survey this wilderness. At the invitation of the government of British Columbia, Alcan sent crews to measure the power available in the area and determine the cost of its development. The manufacture of aluminum is only possible with abundant low-cost power, and today it is an axiom that such power is found only in remote areas. By air, by water, and by land, Alcan crews penetrated the 5,400 square mile watershed of the Nechako River, mapping its unknown terrain, measuring the energy of its uncharted waterways. After 2.5 tough years of investigation, the decision was reached, and Alcan turned toward the west to produce aluminum in British Columbia. The Kitimat project involved 5 separate engineering feats. First, a dam was constructed in the canyon of the Nechako River to impound the waters of a chain of lakes. Second, a 10-mile tunnel was driven through the mountain barrier to give passage to the falling waters. Third, a powerhouse was carved inside a mountain at Camano to convert the energy of falling waters into electrical power. Fourth, the erection of a transmission line to carry the power to the smelter at Kitimat. And finally, the building of an aluminum smelter and port on tidewater at the end of a fjord. Each of these projects was a major engineering feat. Their sum total had never before been attempted by any single industrial company. In February 1951, construction began. At Kitimat itself, in the mud and tangle of the foreshore, the smelter site was opened up. A scene of desolation, but engineers could see beyond the tidal bogs, beyond the tangled undergrowth and rotted trees, a vision of the deep sea port and great smelter to come. At the same time, an army of men and machines launched a 5-pronged attack on the 5,400 square mile drainage basin of the Nechako. From tidewater on the west, up through the barriers of the Coast Range, From railheads far to the north and east, they moved into an area that had known only the transient passage of the Indian, the fur trader, the surveyor. Now, men came into this wilderness to stay, carving roads to move machinery and supplies into the largest construction project ever undertaken by private enterprise. Where it served his purpose best, he reverted to the methods of the fur brigade, the voyageur. Self-propelled barges fought their way up the narrow waterways of the Nechako system to the headwater lakes, where they would serve as cargo carriers. By midsummer of 1952, the Nechako River had been diverted from its course, its canyon stripped to bedrock. Now, 1,000 men were moving a mountain into a canyon to hold back the river. Every 45 seconds, day and night, a load of rock, clay, or gravel was added to the structure. Nature's own materials forming a barrier across the river valley. In 6 months, the task was finished. One of the world's largest rock-filled dams barred the eastward flow of the Nechako, raising the level of the chain of lakes, reversing the flow of an ancient watercourse, conserving energy for a new industrial enterprise. Meanwhile, 150 miles to the west, at the headwaters of the lakes, hard rock miners were carving a new channel for the waters through the rock of the Coast Range. From the head of Tatsa Lake, crews tunneled to the west. From Kamano on the coast, they tunneled to the east, while from a midway point, other crews tunneled in both directions. Driving the 25-foot bore was one of the most spectacular jobs of the Kitimat project. In the 2 years it took to drive 10 miles through Mount Dubose, drill crews broke world tunneling records. Fired, the last barrier shattered, the way lay open for the waters from the high lakes to the sea. Almost at sea level and a quarter-mile inside the mountain, other hard rock crews had blasted out a great cavern for the Kamano powerhouse. In 20 months, they tore out 500,000 cubic yards of rock. The powerhouse was placed underground for good reasons. Limited space in the narrow Kamano Valley, safety from avalanche and rock slides, reduced cost of steel and concrete, and to provide firm foundations for the massive generators. 3 150,000 horsepower generators comprised the initial installation. These were followed at intervals by 4 others. The powerhouse was planned for an eventual 16 units, with a total capacity of 2,400,000 horsepower. Only 50 miles separated the powerhouse at Kamano from the smelter site at Kitimat, but they were 50 of the toughest miles ever traversed by high-voltage power transmission lines. Access to the right-of-way was by helicopter, and later by road. And what a road. Up from the valley floor, up over the mile-high hump of Kildala Pass the towers climbed, sometimes 1,000 feet in a mile. workmen finally conquered Kildala, stringing 2 complete transmission systems of aluminum cables across the dizzy heights to Kitimat. Building an aluminum smelter and port at Tidewater was the main chapter in the story of the Kitimat project. Although it may have lacked the drama of the more spectacular engineering feats, it was nevertheless a gigantic task. Dredging 2.25 million yards of gravel from the ship channel, moving in another 3.5 million yards by truck to raise the smelter site above the tide flats of the delta. 3.5 years of work culminated in late July 1954. Power surged through to the pot lines. This was the start of aluminum production at Kitimat. Since the first ingot was cast at Kitimat in August 1954, continual improvements have taken place in the smelting operations to keep Alcan ingot in a leading position in world markets. Carefully controlled grades of the basic metal pour from these furnaces for general commercial use. Alcan also produces many alloys to meet the specifications of individual customers. The Trilock ingot, weighing 50 pounds, is one of its most familiar forms. Aluminum has characteristics that lend themselves to a variety of manufacturing processes. It can be rolled, spun, drawn, extruded, forged, cast, and blown into powder. These 1-ton bundles of primary metal still have a long way to go before they assume rolls and shapes familiar to the consumer. To meet demands of specialized customers for primary metal in other shapes, new equipment has been installed in the remelt and casting division. A continuous casting process results in round billets 20 feet or more in length. These are used by the makers of aluminum extrusions, where the solid metal is forced through dies to form tubing, angles, bars, and complex structural shapes. The long billets pass to a saw, where they are cut to the lengths specified by the customer before heat treating and final inspection. The Kitimat plant can now supply extrusion ingot in a variety of lengths and diameters to suit any customer. Sheet ingot is also produced. Today, there is a demand for ingot larger than the traditional 50-pound size, so the plant casts special T-shaped ingots of 750 and 1,500 pounds for remelting by Alcan's customers. The plant is a showplace for visitors from all over the world. Casting techniques drew the attention of Lord and Lady Alexander and Mr. Fraser W. Bruce, president of Alcan. Lord Alexander, a director of Aluminium Limited, visited Kitimat en route to New Zealand to officially open a sheet rolling mill using Alcan ingot. Eight of these 1,500-pound ingots contain enough metal to supply 28 city homes with modern aluminum siding. Six tons of metal, the product of enormous quantities of electrical energy, enough electricity to light a small town for several months. But it takes more than low-cost power and tidewater transportation to produce aluminum. It takes people, and people need a pleasant place to live. So the sixth and equally interesting chapter was the building of a town site. The Kitimat of today did not evolve in the traditional way from a few houses and a general store. It is the first stage of the plan for a city drawn up by one of the foremost town planners in the world. It has emerged from the mud-splattered stages of early development as a community of paved streets and pleasant homes. It is not a company town, For although Alcan supervised its birth and guided it through early infancy in the affairs of the self-governing community, the same as any other owner of property, Kitimat is administered by a reeve and 6 councilors, with a municipal manager responsible only to these elected representatives of the people. Before there was a town or people here, the company had to make decisions without reference to future citizens. But as soon as possible, the day-to-day affairs and functions of the community were turned over to the people themselves. An independent weekly newspaper with strong editorial policies reflects a deep interest in the town and its people. And a hospital staffed and equipped to city standards. This is a town of young families, so it has the finest in schools to educate its young people. A great place in which to be a youngster, for all around are the wonders of the unspoiled outdoors. Here is family companionship, in fishing expeditions, or in the quiet of the garden, for this town was built around the family unit. People who work together, play together. Kitimat's list of local organizations, service clubs, cultural groups would do credit to a far larger town. Their activities culminate in a bang-up celebration once a year when the whole population participates in the Dominion Day festivities. Young and old, they all turn out to watch the fun. In the final analysis, it is people who make a town what it is. And here in this young community, there is a rich heritage from the old lands. More than 30 separate ethnic groups are represented, each making its own contribution to a new way of life. Freedoms and pleasures of small-town living, with all the conveniences of a big city. Kitimat has been laid out for progressive expansion into a multiplicity of neighborhood districts such as this, each complete with shopping centers, department stores, supermarkets, and a wide range of specialty shops. Even though it is ringed by the endless forests of the Coast Range, by the mountains and the sea, Kitimat is not a frontier town. It is rather a town with sturdy roots, for the transition from hurly-burly of construction days has long since passed. Where man came into the wilderness to build a modern city, he has succeeded. Here is opportunity for gracious living in a community with a well-secured future. Opportunity to engage in sports or in less active pastimes. Opportunity to enjoy the good fellowship of recreational groups and clubs. Winter can be a season of blue skies and glittering frost. Kitimat is a Tsimshian Indian word meaning people of the snows. And as each succeeding year draws to a close, the people of varied ethnic and religious backgrounds draw together in the true spirit of Yuletide. The vision of 1951 is today's reality. Beyond the mountains, restless waters have been tamed, a watercourse reversed, a town and major seaport built, and a great aluminum smelter now sends its products to the markets of the world. But even these achievements may well prove to be but the opening paragraphs in the continuing story of Kitimat. This industrial enterprise and all that lies behind it, across 200 miles of mountains, has been called a monument to men with vision and faith in Canada. Even now, 1 million pounds of primary aluminum a day move from the smelter to the port for loading into freighters from many foreign lands. Kitimat, world port, destined to grow in stature with the passing years as more aluminum flows outbound to the markets of the world.
Down through history, man has always been a builder, striving to advance the frontiers of civilization into unknown lands for the benefit of himself and his children. One such frontier lies 400 miles north of Vancouver in the fastness of the Canadian mountains. And today, in deep valleys bordering the Pacific Ocean, man is changing a wilderness. The story of his enterprise is the story of Kitimat. It begins in the ceaseless flow of running waters, a myriad of streams that unite into rivers, mighty torrents, racing and surging downward to the ocean. Not all regions of the world are blessed with an abundance of water. But here on the Pacific coast, a vast region of granite mountains, peaks, and crags reach upward, grasping the waters from moisture-laden winds. And beyond to the east, across this mountain barrier, a high-level plateau where the waters collect in a vast lake area half a mile above the sea. In 1928, provincial surveyors made the first report on the tremendous hydroelectric potential of this area. Here was a region of waters that held millions of horsepower. But in the score of years that followed, no one could be found to use its power, and the waters lay idle and wasted to the sea. In 1948, man came again into this wilderness, this time to stay. At the invitation of the British Columbia government, the Aluminum Company of Canada commenced field investigations to find the answers to three important questions. Could 2 million horsepower be developed in this area? Could it be done economically? Was there a tidewater location for a town site where men and their families could dwell, and space for a plant to produce aluminum for expanding world markets? It would take 2.5 years to find out, but surveyors tackled the job with consuming interest. In the skies, bush planes set out on exacting missions of aerial photography, while the largest fleet of helicopters ever assembled for civilian enterprise undertook surveys that would have taken years from the ground. Important in these early investigations were weather studies. Men who would spend lonely months in remote places needed warm cabins. Their jobs would be the most isolated of all. Through long winter months, recording temperatures, measuring snowfall, and checking velocities of winds. Throughout the summer of 1949, the work went on. Rivers, seldom traveled by man, became highways where skilled boatmen carried the survey into the wilderness. Slowly, the unknown country was giving up its secrets. Inexhaustible water, life stream of the Kitimat project, would require a dam to reverse the flow of the Nechako watershed. Crews set up camps, preparing to probe riverbed and canyon walls, seeking firm rock on which a dam would stand against the pressure of the rising lakes. Cables bridged raging waters, giving ready access to either shore. The survey gained momentum as northern days grew shorter, but with winter the work continued. Frozen lakes themselves became communications links, as bush planes maintained contact between the camps and headquarters. At scores of points across the area, sensitive instruments were left to record the story of a winter. And figures collected by engineers became working data for the slide rules of scientists. Scientists who were not content with the fact that water was abundant, but who needed precise knowledge of its flow from the streams and lakes of the watershed. This accumulation of data was to help them calculate the electric power that could be developed. In the Vancouver and Montreal offices of the aluminum company, engineers assembled data and the Kitimat project emerged. 2.5 years of arduous investigations were bearing fruit. Development would not be easy, but engineers said it could be done. Harnessing water and building plants and towns was not new for the Aluminum Company of Canada. During half a century, Alcan built 4 great smelters in Quebec, and there today uses 2.5 million horsepower and produces 1/4 of the world's aluminum. Now, the directors of Aluminium Limited, the parent company, reviewed the British Columbia surveys. McNeely Dubose, vice president of Alcan, went to confer with the Honorable E.T. Kenny, Minister of Lands and Forests, and George Melrose, his deputy. The decision was reached to go ahead with this project on the west coast of Canada. The Kitimat project involved 5 separate engineering feats. First, the Kenny Dam was constructed in the canyon of the Nechako River to impound the waters of the chain of lakes. Second, a 10-mile tunnel was driven through the mountain barricade to give passage to the falling waters. Third, a powerhouse was carved inside a mountain at Camano to convert the energy of the rushing waters into electrical power. Fourth, the erection of a transmission line to carry the power to the smelter at Kitimat. And finally, the building of an aluminum smelter at the end of a fjord. Each of these tasks was a major operation in itself. Their total had never before been attempted. On February 26, 1951, construction on the Kitimat project began with the first access road pushed inland from Camano Bay. At Kitimat, in the mud and tangle of the foreshore, the smelter site opened up. Tide-washed bogs of the delta, a tangled undergrowth of rotted trees. To a layman, an unlikely-looking spot for a huge industrial enterprise. But aluminum needs tidewater for transportation, and the engineers could see beyond the desolation. Their eyes saw in raw land the vision of the smelter to come. This was tough country, hard to clear, difficult to make habitable, nearly impossible to traverse on foot. But despite the dismal scenes of early access, man gained in his battle against the wilderness. Construction camps sprang up to prove that he had come to stay, while executives of the company directed their full attention on the 5 major phases of the development. First among these was a dam across the Nechako River. On the eastern perimeter of this area, man had started to reverse the course of a mighty water system, had stripped the canyon of the Nechako down to bedrock, and prepared the area for the building of the Kenny Dam. And now, 1,000 men and their machines were moving a mountain into the canyon. Every 45 seconds throughout the summer of 1952, one of this fleet of trucks hauled a load of material into the canyon, building a man-made mountain to hold back a river. It took 1,000 men 6 months to fill the dam with rock, gravel, and clay. Clay dug from nearby pits was used as the core of the dam to seal the structure against the pressure of rising waters. Experience of foremost engineers in the world lay behind the design and construction of this dam. Every layer, every strata of materials carefully controlled. Layer upon layer, the zones of sealing materials were built up, only a few inches at a time, then carefully tamped into a solid mass by heavy machines called sheep's foot rollers. The engineer's plans showed a structure as wide as it was long, in power than the pyramids of Egypt. The passing of time and even earthquakes would only tend to settle the dam more firmly into place. Throughout the summer of 1952, this army of builders worked to complete their project before winter set in. In 6 months, they had moved a mountain, rising 317 feet from the riverbed, measuring 1,550 feet from one side of the canyon to the other, one of the largest rock-filled dams in the world. In the autumn of 1952, the task was finished. The tunnel, which had diverted the water while construction was in progress, now could be closed. On October the 8th, the gates were slowly lowered. Storage of water began. The first major objective in the Kitimat project was achieved. Inch by inch, water crept across the toe of the new dam. Water that had flowed unchecked for centuries began to conserve energy for a mighty enterprise. 150 miles to the west, at the end of Lake Tatsa, another construction camp had been set up. A community of hard rock men and their families were settled down to a 2-year task driving a tunnel through a mountain. And the record of the Camano Tatsa tunnel is the second chapter in the Kitimat story. The Camano camp at the west portal of the tunnel reflected the magnitude of the work going on inside the mountain. A camp city of 3,000. Carpenters and steel men, electricians and truck drivers, and the important hard rock men of the project. Camano crews tunneled toward the east. Tatsa crews tunneled toward the west. Still other crews drove in both directions from a halfway point. These were the men that broke world tunneling records, who could drill 100 holes 15 feet deep in less than 2 hours. After the drilling, the charging of the tunnel face. Drill holes filled with explosives to blast away the granite, to make a new channel for the waters to come. The charging finished, now came the wiring of the charge, connections to a switch 1,000 feet down the tunnel. Now the face is cleared, ready for the blast. And now, after each blast, the shattered rock was hauled to the dump. Driving the 10-mile tunnel was one of the spectacular jobs of the Alcan project. Drill crews at 4 headings competed eagerly, and 3 times world records were broken. The last, when crews at 1 heading tore out 282 feet of tunnel in a single week. Day after day, for 21 months, barmen emptied their mine cars on the dumps, while engineers checked off the days to the time when the tunnel would be completed. The breakthrough day finally arrived. The last hole had been drilled. The last round was set. McNeely DuBose fired the final charge. In the early morning hours of December the 2nd, 1953, the final barrier between the mountain, lakes, and the sea lay shattered. A single moment of elation came to men who met in the breakthrough, congratulated colleagues whom they'd never seen. Soon the surging water would flow through this tunnel to generate electricity. These men had driven one of the world's great tunnels. Their path for a river through a mountain was ready. And here, 5 miles underground, the second chapter of the Kitimat story came to an end. But in the meantime, Chapter 3 was unfolding in the powerhouse. Work on the powerhouse, a quarter of a mile inside the mountain, began in the fall of 1951. And in the 22 months to follow, 500,000 tons of rock were taken out. Enough rock to fill a fleet of trucks stretching for nearly 800 miles. Like others throughout the world, Camano Powerhouse was put underground for good reasons. Limited space in the narrow Camano Valley. Firm foundations for massive generators. Reduced costs of steel and concrete. Safety from snow and landslides. Construction men on the project threw themselves wholeheartedly into the job, while their children enjoyed life in the wilderness. They had many advantages of the city, including school. And for free time, there were playgrounds in the woods and streams of the great, clean outdoors. In due course, the powerhouse was ready for the installation of the first 3 generators, the world's largest. Each would produce 150,000 horsepower. These machines would generate the continuous flow of electrical energy, the vital power needed to make aluminum. Aluminum, a century ago, was a rare metal. Today, because of electricity, it meets a world demand as one of our most useful metals, and a metal of particular significance to Canada, where water resources can generate the economical power needed to refine aluminum ore. Experienced, subtle hands assemble the great power plants, generators that turn the moving water of captive lakes into a useful force. The great cavern, already 700 feet long, can be readily expanded to produce more power. Space remains for 5 additional generators. And when the ultimate capacity of 2,240,000 horsepower is required, the powerhouse will be extended again to hold 8 more generators. And a second tunnel will be driven from the lake area to serve them. Here was an industry making vast preparations for its first production. But once established, an industry able to expand rapidly to meet the world's demands for more aluminum. The first generator went on power on July 15th, 1954. Chapter 4 of our story is about the transmission line to Kitimat. While men prepared to make power inside a mountain, others opened the way for transmission of that power to Kitimat. Access to the transmission line right-of-way across the mountains and crevasses of Kildala Pass was gained by helicopter as well as by road. This was tough country to traverse and tough country in which to build. Up from the valley floor to the hump of the Kildala, up from a quiet valley to the wind and cold of a mile-high pass. To reach the summit with sections of transmission towers, construction men had to build a road. And what a road it was. Only 6 miles to the summit, but rising sometimes 1,000 feet in a mile. Around sharp switchbacks, above ledges, beneath overhanging cliffs. This was a frontier road, cut and hacked and blasted up a nearly impassable mountainside. The Keldala Pass had been crossed by a road that was in itself a monument to Canadian engineering and one of the most difficult feats of the entire project. And now, transmission towers mark the rugged trail from Camano Powerhouse to Kitimat. Here, a mile above sea level, the last of 300 towers was erected. Men swung over dizzy heights, completing structures to hold the world's largest aerial transmission cable, jobs for sure hands and steady heads. As the towers were completed, the cable stringing began, aluminum cable with a steel core. Big drums paid out this line that would soon carry power across the pass to Kitimat. Brake rollers holding the cable to a calculated tension. A job of precision requiring judgment and experience. In due time, the 50 miles of transmission line were completed. And on July the 15th, 1954, first power surged across the mountain to Kitimat. We come now to the main chapter of the project, Kitimat itself. In the broad, tree-covered valley of the Kitimat was room for the smelter and room for it to expand as the demand for aluminum grew across the world. Room for the plants of other industries attracted by electric power and a deep-sea port. Room for a town site growing with churches and homes and schools as the community grew, developing as its people wanted to develop. And running 40 miles up the valley to Terrace on the Canadian National Railway, a rail line connecting Kitimat with all parts of North America. Construction of the Kitimat plant commenced early in 1951, and for 3 years, engineers and executives of the company watched its progress closely. By the summer of 1953, the rising smelter presented a startling contrast to the wilderness of scant months before. Man had applied his mind, established new frontiers. Soon, the distant waters would yield their hydroelectric power to make aluminum. Countries short of abundant power would have a new source of the strategic metal, useful in peace, vital in war. At Tidewater, a massive dock was needed to receive ore from Jamaica and to load freighters carrying aluminum overseas. Huge reinforced concrete caissons were constructed inside a coffer dam. Now the dike was breached and the massive piers built on dry land were to be floated into open water, widening the breach and waiting for the tide to lift the massive hulls. Each weighed 7,000 tons, a heavy strain upon tow lines and tugs. One caisson gone and two to go. This was the sort of engineering achievement typical of the Kitimat project. Section 2 followed on the next high tide. Sunk into position a few days later, the 750 feet of new wharf became the stepping stone to the aluminum users of the world. The builders of Kitimat came from all parts of Canada and the United States, and some from overseas. They brought with them healthy appetites of outdoor workers, and they thrived in the temporary housing accommodation of construction camps. But the permanent smelter workers and their families would need permanent homes. A community started to grow on the new town site. As in every part of the project, the town site was surveyed and planned before Earth was broken. Most cities grow from small beginnings, without imagination or plans for the future. Alcan had the wish and the will to house its people well. Expert town planners and architects spent months perfecting on paper a city which might someday grow to 50,000 people. Space was marked for air and sun and trees, space where no buildings must ever rise. Sites assigned to churches, schools spaced out, streets plant tidy homes. The homes of Kitimat, built with the benefit of foresight, placed with the skill and convenience of modern planning. The sign of a permanent community, homes with a heritage for the future. As homes became established, the provincial government of British Columbia issued a charter to the new community. People cast their votes in the first poll of the district. By secret ballot, they elected the first governing council. Elected officials voted, and a community of men and women faced their future with new stature and authority. Civic government became a reality at Kitimat. By August of 1954, the power resources of a vast wilderness had been harnessed. 450,000 horsepower waited to serve mankind. And the first 2 units of the smelter were ready for operation. The Kitimat project was ready for smelting of the first aluminum. On August 3rd, 1954, His Royal Highness the Duke of Edinburgh visited the Kitimat project during his tour of Canadian industry. He was welcomed by Mr. R.E. Powell, president of Alcan. Executives and engineers of the company were presented to him. His visit was the event of the year for construction workers and their families who had seen the project grow. Inside the smelter, pouring of the first ingot of aluminum coincided with the Duke's visit. An historic moment as the first aluminum made in Kitimat poured into its mold. Here, the culmination of years of work and planning. Here, the first step in the movement of a new supply of aluminum to serve mankind. This quiet ceremony started off the first year's production of 91,000 tons, an output that will soon be increased to 150,000 tons. Aluminum for the free world. This is a story of origins and beginnings. The Kitimat story has many chapters yet to unfold, for nowhere in the world can aluminum production be expanded more quickly and economically. Beyond the mountains, lakes are waiting, storing their abundant energy, while a power cavern with 3 generators has provision for an ultimate capacity of 2.25 million horsepower. Power that will surge along a proven right-of-way and over the pass to Kitimat. Even as aluminum flows into world markets from the 2 smelter units first in service, expansion is underway with 2 more. And eventually, 12 units will produce over 1 billion pounds of metal each year. Aluminum for the modern way of living. Out of a wilderness, a new industry has come to life to serve the free world. Its progress will be recorded in future chapters of the Kitimat story.